All right, any questions? No? We're going to continue we were talking about last time. So the single replacement form has some exceptions that memorize. It's easy, single replacement form, but if you have to memorize exceptions or you have to figure out exceptions, then it makes it much more difficult. So alternatively, we can just do another method, which is, let's see, A, B, C, D. This would be the chart method. The chart method does have drawbacks too. You know, sometimes things aren't on the chart. But this turns out to be a good method to do it. Let's just do an example here. If we did silver plus nitric acid using the chart method, what we do is we first determine the major species in solution. Okay. So determine major species. You know, here we look at things like the solubility rules and electrolyte properties. You guys remember electrolyte properties? Electrolyte properties are what? What are strong electrolytes? Not the metals, but you know, the strong electrolytes are the. Well, what do strong electrolytes do? Not that. They conduct electricity. That's one way of thinking about electrolytes, but we're going to use the other definition of electrolytes. There are two definitions of electrolyte. You know, one definition is electrical conductivity, but we're not conducting electrons. Do you know what we're conducting? Ions. You know, ions are the charge carrier here. Ions. And so we got electrolyte properties, electrical conductivity. That's one definition. The other definition is that they dissociate, you know, almost 100% into ions, right? Dissociate almost 100% into ions. This is the definition we're going to use, you know, here. This one is more for electrochemists. Okay. Now, what types of species? Well, you know, if they dissociate almost 100% into ions, we call those strong. Right? But some things don't. You know, some things partially dissociate. If they partially dissociate into ions, we call them weak. And if they do not dissociate, we call them non. Okay, not dissociate. So you should know, what are the strong electrolytes? So this should be automatic, you know. This is something from Chem 4, it should be automatic. Should have it memorized. What are the strong electrolytes? Not the metals, the strong electrolytes. Strong electrolytes. No? Don't remember? You know, don't remember then, you still need a lot of that Chem 4 stuff, so good thing to do is review. Just flip through your notes, the Chem 4 stuff. The strong electrolytes are the strong acids, strong bases, and soluble salts. You know the strong acids? You should know the common strong acids. What are they? Yeah, hydrochloric, hydrobromic, etc. Yeah. How about hydrofluoric? Is hydrofluoric a strong acid? No. So it's not. What are the weak electrolytes? Weak electrolyte. Weak acids, weak bases, and the not the insoluble salts, some heavy metal salts. And so weak acids, weak bases. Some heavy metal salts. Everything else will be the non-electrolytes. Everything else. That's it. All right. Okay, what else do we want to do? Well, we look at the major species here, and so the major species will be silver metal, and then H+, and then NO3- in water. Those are the major species present. We call this the inventory. What we'll do is we'll inventory the what's present. And so I see 4 things. H+ is the same as H3O+, talked about earlier. Okay, then what you do in the next step is you just consult the chart. Oh, actually, that chart's hard to read over there. I'm going to put up the chart here. About that. On the projector. The chart in our book, I don't know if anybody's looked at the chart in our book. Probably not, because the chart in our book is in the Appendix D. So probably don't use Appendix D or haven't used it. But take a look at Appendix D because there's a lot of information in Appendix D. We're going to be using it a lot this semester. The Appendix D chart is, I think, 5 pages long. And you'll notice something different about Appendix D chart than our room chart. Appendix D is flipped upside down compared to our room chart. And so this is what leads to a lot of confusion because a lot of people say, oh, if it's higher, well, higher is totally irrelevant in the chart. Higher or lower. When people say higher or lower because they're used to the activity series, is it higher in the activity series or is it lower in the activity series? But if the activity series were flipped upside down, like it is in our book, then you might have some problems. And the activity series is flipped upside down in Appendix D. We could use any redox chart available. Pre-1980s, that was the common one. Post-1980s, the one in our book. Actually, 1990s. 1990s is flipped. But
nobody cares because, you know, whether it's flipped one way or the other, so, I guess somebody cared. They cared enough to flip it, but nobody who uses it really cares, you know, because it's so easy to use either way. And I saw no need to flip it. Looks like a good one. I haven't seen this one before. Only problem with this one is it's a little thin. You know, there's some stuff missing out of this one. Sulfuric acid's there. Do you see sulfuric acid? Right here. But nitric acid is not here. Well, it's too bad. It looks like a decent one. Let's get something more comprehensive. Boy, this one is even flipped and reversed. That's okay. It's better because this is the standard way it's written. Can you guys read this? This one has a lot more species than the one that I'm going to hand out, but that's good. Oops, come on, let me scroll this. Resolution isn't that great, but take a look. What's at the top of the chart here? Fluorine. Fluorine, you know, as what? An oxidizer or reducer? And you should know something special about fluorine. It's the strongest oxidizer on the chart here. Number 2 is different than our number 2. You know, number 2 over there is, what is it? Hydrogen peroxide. This number 2 is, can you read that? What is that? It's hard to read. Can you see it? Blow it up more. Ozone. Ozone and acid, right? Number 3 is really weird. What is number 3? What is that? Yeah, you know, because that O is kind of distorted. That's cobalt 3+. It kind of almost looks like carbon monoxide 3+, doesn't it? It's cobalt ion 3+, which turns out to be well, not cobalt 3. You'd think, that's a common oxidation state for transition metals 3+. You see lots of those, right? And cobalt 3 is not so happy. Cobalt 3 turns out to be a very powerful oxidizer. More powerful than hydrogen peroxide. This is an interesting one. This is lead 4 oxide. You know, lead 4, when we get to these kind of heavy metals, we see a lot more covalent bonding than ionic bonding. This is not lead 4 ions necessarily. There's a lot of covalent interaction, a lot of sharing, so the charge doesn't get as high. So the oxidation state is +4, and this is much more covalent than lead 2 oxide. Lead 2 oxide is much more ionic. Heavy metals, you know, heavy metals occur, a lot of them occur in this semi-metal region, right? The transition between, you know, metal, non-metal, ionic bonding to more covalent bonding. And so we see. All right, and so all we do is we consult the chart. You know, this method is so easy, but since it's not in the book, a lot of people think it's so difficult. Anything that doesn't appear in the book is impossible to do, according to some people. But you know, a lot of people find this method easy because you don't have to know anything about redox to do this. You probably can train like an elementary school child to do this method, you know, because they don't have to know any chemistry to do it.
is all you're doing is you're looking for this species here on the chart. Does this species occur on the chart? And so we look for it. We go down the left side. Oh, I see it. Is this it here? No, that's not it. Why? Because it's an ion. Is that an ion? No, well, it's close enough. You know, sodium metal, sodium ion, same thing. Is it? Sodium metal, sodium ion, same thing? No, totally different, you know. And so that's an ion, so no. But we see on the other side, we have the metal. On the left side, we have what are called the oxidizing agents. On the right side, we have the reducing agents, because these reactions are reversible. And so if we go backwards here, then silver metal loses an electron to form silver ion. We don't need two charts. We don't need a chart of oxidizing agents and a separate chart for reducing agents. Do you know why? Why don't we have a separate chart? One chart for oxidizing agents, a second chart for reducing agents.
The strongest oxidizing agent up here will have the weakest reducing agent.
Yes, it goes both ways, plus the conjugate relationship. And so, yeah, exactly. The strongest oxidizing agent, its conjugate will be the weakest reducing agent. Fluoride does not want to lose an electron, right? Fluoride absolutely does not want to lose an electron, so it's going to hold on to it very tightly. That means this is very weak for a reducing agent. Silver, well, silver ion is a decent oxidizer. We got silver metal. And so we consult the chart. And so we say that this is a reducing agent because it occurs on the reducing agent side. And then all we do is we go next. The next thing would be H+. So we look for H+ here. I see H+. Right here, there's H+. Can I use this equation? I can't use this equation because there's no ozone. Oh, I see another H+ here. How about this H+? I know there's O2 in air. Can I use this one because there's O2 in air? No, because we aren't bubbling. We would need to bubble the air in there. Actually, if we read the chart, this should be O2 at 1 atmosphere. So we go down, down, and way down here, I finally see H+ alone. Here's two H+ plus 2 electrons, so this is what we call an oxidizer. Away. And then I go to nitrate. So I saw nitrate up here. Nitrate's a pretty strong oxidizer. Here, is this chart legible? Can you guys see it? This is nitrate, but you know what? I need H+. I have to have nitrate and H+. Well, nitrate and H+ is called nitric acid. But you notice it's not balanced because I should have 4 H+ and 4 nitrates. You don't have to worry about that, you know, because if we have nitric acid, that means maybe 3 of the nitrate ions will be spectators, 1 will be a reactant. You know, we just have to react in this ratio, nitric acid. So we're going to have some leftover nitrate, but it's all right. And so do you see that? Well, it just so happens we have H+ present and nitrate. This is an OA. So this is what I think your book and some other books call a synergistic relationship. You know, nitrate alone is not that powerful. H+ alone is not that powerful, but a combination of nitrate and H+ is powerful. And nitrate alone is still decent. All right, then we go to water. Do we see water on this chart? Water is present as a solvent. Normally people ignore the solvent. Oh, I see water right here. Can I use this water? No, because I don't have any permanganate. Let's go down here.
see water here. Do you see that? Water. So that's on the oxidizer side. This is the problem that happens all the time. A lot of people are so unfamiliar with this chart, you know, that they don't know that water occurs on both sides. They've never really read the chart fully. And so one of the things that you'll see when you actually read the chart is that water does occur on both sides of the chart here. Do you see it here? And so water can be a reducing agent. And so have you heard of amphoteric species? Obviously you have, I hope so. Amphiphilic, amphoteric. Yeah? It doesn't ring a, if it doesn't ring a bell, boy, you know, in the future, let me give you some advice. Review, you know, when you're taking a sequence of classes, as you get into the higher classes, you know, they don't really spend much time reviewing. You know, Chem 1A we do. But, you know, most of the classes I took, you know, you should review some of the basic stuff. But amphoteric means it can go both ways, right? Water is amphoteric. Amphoteric means it can act as both an acid or a base. Well, there's the same thing, but there's no fancy word for it in redox. A lot of species can go both ways. Water is one of them. Name one other. Name one other species that can go both ways. It can either be an oxidizer or it could be a reducer. Well, that, you know, you'd look up on the chart and then see, you know, see if you could figure it out. You know, and then once you do that, then you can name a lot of species that can do it. Like carbon, you know, carbon can give up electrons, carbon can gain electrons, but things that aren't on the chart, you'll figure out. Initially, you'll want to see the ones that are on the chart. It can go both ways. The reason I bring this up is because, you know, on tests, I like to give it and then see how many people get it wrong. And every semester, a lot of people get it wrong because they think it only goes one way. It goes both ways. One of the most unusual ones is hydrogen peroxide. Everybody thinks of hydrogen peroxide. Look at it. Hydrogen peroxide is the second most powerful oxidizer up there. But unusually, hydrogen peroxide can either gain or can lose. It's really weird. That doesn't mean they're equal. Like, for example, water as an acid or base, it's equal. It can go either way. It doesn't matter. But, you know, hydrogen peroxide is a much more powerful oxidizer than it is a reducer. There are others as well. All you do is you look at the chart and then you think, you know, if it's not at the limits, you know, one way or the other, then it can go both ways. If something's between the limits, that's something you'll see. Anyway, what we do next is we consult the chart, then we choose the strongest OA and RA. We choose the strongest because the most likely reaction to occur will be between the two strongest species, the one who wants the electrons the most and the one who will give up the electrons the easiest. And so looking at this, all we do is we know how to rank these. Let's start off with the oxidizers, because oxidizers are on the left side of the chart. And so we'll look for these three. We have three oxidizers here. And so all we do is we start off at fluorine and then work our way down until we hit the first one. And so starting off at fluorine, what's the first oxidizer I'll hit? Down here. The first oxidizer I hit is nitrate with H+. The others, H+ is way down here, and H2O is near the bottom of the chart. As you'd expect, H2O is not very reactive, right? And so the strongest oxidizer present will be the combination
here. H plus and nitrate, or nitric acid. This will be our strongest oxidizer. And then we pick our strongest reducer. We have 2 reducers present. And so what's the strongest reducer on the chart? I asked you to memorize it. 2 anchor points, right? Have you memorized it? Lithium, good. And so we start off at lithium and then work up. What's the first one we hit? Here's silver metal. It's silver metal but with chloride, which is a stronger reducer than silver metal alone, which is near the top there. And that's because it forms a more stable product. Take a look at the product here, silver chloride versus silver ion. Silver chloride is a more stable product. Even though chloride, no redox occurs with chloride. So the first one we hit is silver, and then water's up here. Not a huge difference, but it looks like silver it will be our best producing agent. And so the most likely reaction to occur will be between these 2 species. And then what we do is we just react the 2 species. And so essentially just copy equations and add. And so let's just copy the equations off the chart. Well, copying the equations off the chart, we got nitrate plus 4H plus 3 electrons yields NO plus 2 H2O liquids. NO is gas. Oftentimes I'll omit the aqueous because so many things are aqueous. If I omit aqueous, then I'm going to make sure I write gas, liquid, solid. And so if you don't see any state there, that just means it's aqueous. That's just to save myself some writing. You're welcome to do the same thing. So I just copied that. Now I got to copy the equation for silver, right? So I copied the equation for silver. Tell me the equation for silver. Well, it's right here. Okay, how should I write it? Should I write it Ag plus an electron? No, good, you guys are on it, because Ag plus is not a reactant. What is the reactant here? Ag. So what I have to do is I have to flip this equation backwards. Otherwise, I don't have it right. A lot of people just like to copy it, but we have to reverse this one. This one must be reversed because we have silver, not silver ion. So we had to reverse this one to form Ag plus an electron. Now, if we had Ag plus, we would just write it as is because Ag plus is a reactant. So here are our 2 reactants, right? Silver metal and nitric acid. Those are 2 reactants. Water turns out to not be a reactant because it's too stable in this particular case. Okay, then we add. Well, how do we add this? We got to add it so that the electrons do what? Yeah, the electrons have to balance out, and so let's go ahead and do that now. Let's get a different color pen. All the pens have disappeared. So what I would do is I just multiply this bottom one by 3, and then it would balance out. And so let's go ahead and add those 2 up. And so we got nitrate plus 4H plus 3Ag solid yields NO gas plus 2H2O liquids plus Ag plus 3. Yeah, and then the 3 electrons cancel the 3 electrons. I'm not even going to bother writing those down to save myself a step. Are we allowed free electrons in the net reaction? No. Right? If you're getting free electrons left over, then you've misadded it, or you need to go back and fix it. How should we check this? Is there a way to check this? We got to make sure the atoms are balanced and the charges are balanced. So nitrogen, nitrogen, 3 oxygens, 4 hydrogens, 3 silvers. We make sure the atoms are balanced, and we make sure that the charges are balanced. So -1 plus 4 is +3, +3 and +3. It's balanced. Okay, we aren't done yet because this is the most likely reaction to occur, but we need a driving force. What's a driving force? Somebody explain to me in one sentence what a driving force is. The reason why a reaction takes place. And so what is that reason? Formation of something? Yeah, formation of? No, not in redox. Formation of the gas is only for metathesis. The reason do you know the reason why I divided the reactions into 3 types? Those 3 types? Is because all redox reactions have the same driving force. But all combination reactions do not. Combination reactions will have multiple driving forces depending on what type of combination reaction it is. And so that, to me, doesn't make sense to divide it into that category, because then you have to subdivide it into further categories, right? Which most people don't do. Most people think it's a combination is a combination. That's wrong. And so all redox reactions have the same driving force, all metathesis reactions have the same driving force, and all acid-base reactions have the same driving force. And therefore, it makes it much easier to predict because you're only looking at one driving force. So if you're looking for gas formation, then we're done. This forms a gas. But redox, it's irrelevant if there's gas formed or no gas formed. I'll give you one that forms lots of gas. If I take 2 liquid waters, 2 liquid waters will form 2 hydrogen gas plus an O2 gas. And so if I start off with 2 moles of water, 2 moles of water is 36 milliliters. If I start off with 36 milliliters, I'll end up with about 75 liters of gas. That's a huge driving force, isn't it? So does this reaction occur? You get 36 milliliters of water, and then all of a sudden you're going to get 75 liters of gas? You didn't get that? No. And so, you know, well, it's a decomposition reaction. Isn't decomposition reaction driving force gas formation? For some it is. For others, it isn't. And so, you know, that system doesn't make sense, the organizational breakdown of that system, the Chem 4 system and Petrucci. Petrucci, you know, it's okay if you want to keep track of all that, but even Petrucci doesn't get into it enough. And so, you know, a lot of people think, well, it's not in the book. If it's not in the book, then it's too hard, right? I'll tell you, what's in the book is much harder. The way that thing's organized. To properly understand it and properly use it is way harder. This is going to save you a lot. Way harder. Because I'll tell you, you know, one of the reasons I organize the reactions this way is because, you know, I'm a chem major. So at UCLA, I had an oral exam. This is like my, I don't know, I had an oral exam there, and I got asked one question, you know, what are the chemical properties of phosphate? You know, and you know, not only did I know Petrucci, I used Petrucci when I was a student at Santa Barbara City College, and then I bought the other book, True Blood, which is the Chem 1 book at UCLA. I read both of them. And so I knew those books pretty well, because UCLA I felt like I was far behind, so I thought my preparation wasn't good. So, you know, I started reviewing during class. All this is why I say, you know, this is why I'm kind of surprised, because you guys should be reviewing as well, automatically, if the stuff is fuzzy, you know. And so I started reviewing when I was taking my classes, the earlier stuff that I felt pretty weak on. And then I got hit with this question, and I knew the reactions, you know, certain reactions like acid-base neutralization and this. But, you know, I'm standing up there, I'm thinking, what are the properties of phosphate? You know, and it's like, there are, I think, how many were there? There were like three people asking questions, you know, just me standing alone in front of 3 people.
And then just dead silence. Dead silence. And the minutes go like tick, tick. Well, thinking, trying to think, you know. Well, then I said, well, you know, phosphate occurs in detergents, you know, because I wanted to say something, but, you know, I didn't have, you know, I didn't have anything organized in my head. Here I'm a chemistry major. I can't even say what the chemical properties of phosphate, a very common chemical are. And so anyway, well, then I went back and looked. I went back and looked at the book. The book was too hard. The book was worthless, basically. Well, anyway, you could, of course, you can find advanced books, you know, that talk about phosphate alone, give you hundreds and hundreds of reactions. That's not helpful either. So after this, hopefully it'll be an easy question to answer, you know, because you know there are three types of reactions. Should have considered. I should have considered redox. What are the redox properties? Well, phosphate plus 5 oxidation state could be an oxidizer, probably a mild oxidizer because it's not one of those ones on the chart, right? It's a common chemical but not on the chart, so my presumption is that it's mild. Otherwise it'd be on the chart, right? Phosphoric acid would be much more dangerous chemical. But I'm sure it's a decent oxidizer though. You know, that kind of stuff. Whether it's the metathesis, well, phosphate will precipitate out with everything except phosphates will precipitate out with everything except group 1 and ammonium. And so everything else, barium it precipitates out with, iron, and everything else. Phosphate is a good base. It's a tribasic base. We'll talk about tribasic bases later. The phosphate is a pretty decent base, as we'll see on the base chart there. Phosphate is borderline strong base. Did you know that? It's right at the border. It's almost a strong base. Okay. Well, it would have been an easy question to answer if somebody had taught me this, you know, when I was a student. But nobody did because none of the books are organized like this. It didn't figure it out until I started taking advanced synthesis classes. And then in advanced synthesis classes, it's organized like this. And then I thought, oh my God, that's so easy. Why wasn't everything organized like this from the beginning? Okay. Well, anyway, we're not quite done, and I erased the key thing because you need to consult this. We need to find out if there's a driving force present. And so what letter are we on? What number are we on? 6? 5? Driving force. All right, so how do we figure out what is the driving force for redox?
Is it electrical potential?
It is electrical potential, but it's too physics. It's too much physics. Let's talk about.
Like electrons transfer?
Yeah, let's talk about it in easy terms. I told you an elementary school kid can do this method. I have no doubt about it. An elementary school kid can do this method. And so let's keep it to the level where an elementary school kid can do it. No, we don't want to deal with oxidation states. We don't want it to have to understand any chemistry. We just want to be able to use the chart.
You just add the subtract the number for the potential from one.
No, we aren't going to do this. Chem 1B. We'll do that when we talk about quantitative. This is very qualitative, Chem 1A.
And then about the electrons.
No, what's the driving force? Didn't I write it down last time? Yes, I did write it down for single replacement, didn't I? Yeah, but I said the activity series was get away from the activity series because we're going to start thinking about. No, I didn't say. No. Yeah, it's more stable. That's a driving force in general, you know, stability. And so, you know, things like a strong oxidizer, what we say is strong oxidizers are unstable, right? Strong oxidizers are unstable, highly reactive. Weak oxidizers are stable, not very reactive. And so what we want to do is we want to go from less stable to more stable. So we go from strong to weak. We go from, the driving force is going from stronger oxidizer, stronger reducer to weaker oxidizer, weaker reducer. And so we have to look, flip back, can you flip back to skeleton redox in your notes? How did we figure out what the oxidizer and what the reducer is in skeleton redox? Did we use the net here? Did we use the net? No, the net wasn't the easiest. What was the easiest place to determine the... Did I talk about that? Is it in your notes or not? The half reactions is the easiest place. If you look at a reaction like this, tell me all the oxidizers and reducers. Maybe it's easy on the left side, but on the right side, it might be more difficult, you know? What's the oxidizer and the reducer going backwards? Because this is a competition, you know? Which side is more stable? If the products are more stable, the reaction is going to go. If the reactants are more stable, then the reaction is not going to go too much. Barrier. Okay. And so we look at the half reactions. The half reactions are the easiest place to see it. And so, I don't know why I erased it. I'm going to rewrite it. Nitrate plus 4H plus 3 electrons yields NO plus 2H2O liquids. Ag solid goes to Ag plus an electron. All right, assign it for me. This part, the elementary school kid might have difficulty assigning it because they'd have to know, you know. So far, we just looked at the chart, copy, you know, look at the chart, see what side it's on. But over here, we already know this one, right? This is well, it occurred on the left side of the chart, so you could call it oxidizing agent. Or you could train the student to say, if the electrons are on the left side, it's a reactant, it's gaining electrons, that means it's a oxidizer. Right? Gaining electrons is oxidizing. Have you ever heard of this? This is going to confuse people, but oil rig, right? Oil stands for oxidation is loss. Why is oxidation gain here? Because the reason is we're not looking at oxidation, we're looking at the oxidizing agent. The oxidizing agent causes something else to become oxidized, you know? This would be like the, this would be something like the robber is robbed. Is the robber robbed? Did the robber get robbed? No, the robber robbed somebody else, right? Is that right? And so this is the same thing. The oxidizing agent oxidized something else. These electrons came from somewhere else. Where did electrons come from? They came from the reducing agent. You see, we're just doing the same thing we did with the skeleton redox, right? And then, what about this one? Oh, that's not NO2, that's NO. Sorry. Well, going backwards, this must be the, yeah, we know the conjugate relationship, right? And so, all we do is we just compare, you know. Are we going from a stronger to a weaker, or are we going from weaker to a stronger? Which side's more stable? Because weak is more stable, right? And so what is a stronger oxidizer, nitric acid or silver ion? So all you do is you go to the chart. You don't have to have this memorized. We start off with the strongest, which is fluorine. And then we work our way down. And it looks like the first one we hit is here, which is nitric acid. Silver ions are below. to weaker. And so what we're doing is we're going from stronger to weaker. And so this is stronger oxidizer to weaker oxidizer. Because of the conjugate relationship, the reducers must be the same. If they aren't, then something's seriously wrong. But we'll verify it. That must mean that silver is a stronger reducer than NO and water. So let's go down. Lithium. We're going to go up. First one we hit is silver. There it is, silver, and then at the top there's NO and water. So silver is a better reducer. So that makes sense here. Silver is a stronger reducer than NO and water. NO and water is a weaker reducer. And so here we have a driving force. The driving force is going from stronger to weaker. From stronger, less stable, to weaker, more stable. That's the driving force. And so the single replacement gave us the wrong prediction. Single replacement predicted that there was no reaction here. In fact, there is a redox reaction. We're going to form a toxic gas, NO. And actually, what was it? The beginning of chapter 4 had this similar type of reaction where nitric acid was generating some kind of brown gas. Did you see that? Nitric acid, copper penny and nitric acid. That brown gas comes from NO being generated and forming NO2. Except in this case, we aren't reacting a penny, we're reacting silver metal. So don't put a dime. Are dimes still made out of silver? Surface? Don't put a dime. I don't think dimes are made out of silver anymore. So, impossible, this method, is it impossible? You know, no matter what, every single semester, I get like 5%, maybe less than 5% who absolutely refuse to learn this for some reason. And so this is why I keep saying, you know, you give it a shot. After you do 2 of them, they're so easy, you'll agree. I don't know. It's weird because you know, a lot of classes that I took, the professor talked about a lot of things that weren't in the book. Lots. You know, and does that mean I can ignore it? I don't need to take notes on this. No, it means you have to take a lot more notes because if it's not in the book, you gotta figure it out. All right, let's consult the chart method of redox there. Now we have a hybrid. The hybrid method is going to be, of course, more difficult. The hybrid method might be, some stuff might occur on the chart. And actually, let me take a look at what we might have on the chart. Okay, so an example might be, you know what I'm going to do? I'm going to take some HCl plus potassium permanganate plus ethanol. Ethanol is very soluble in water, so all these species are AQ. But just to emphasize, I'll write AQ this time. AQ yields what? Sometimes there's what we call multiple reactions that can happen, you know, competing reactions. So for example, HCl and potassium permanganate, if we look at that combination, if an HCl and KMnO4 reacts, this looks like a double replacement reaction, right? This should form KCl plus HMnO4. And in fact, this should have a driving force, right?
What is the driving force for this? Well, in double replacement is gas formation, precipitation, or stronger acid to a weaker acid. So here we are. We're going from a stronger acid, HCl, to a weaker acid. Well, what's that weaker acid's name? No, name the acid. Name the acid, HMNO4. Name the acid. This is, you know, I didn't spend much time talking about nomenclature because I figured you guys can figure it out yourself. Permanganic acid, that's right, good. So we're forming permanganic acid. Permanganic acid is not one of the 7 strong acids, so likely it's a weak. But you know, there are many more than 7 strong acids, right? In fact, there's stronger acids even than the strong acids, super acids. But they aren't that common, you know. Just people who work in those particular fields will deal with those. But let's take a look at this. Okay, are we done? No, you know, that's a double replacement. We usually have some kind of system, so, you know, this reaction can occur, but there's another reaction that will occur. And the other reaction will be more dominant. The other reaction occurs. What is the other reaction? Well, let's look at redox. If we would look at redox, we go, okay, we got H plus, Cl minus, K plus, MnO4 minus, and ethanol, CH3, CH2OH. Then we consult the chart, you know, H plus is an OA, Cl minus is an RA, K plus is an OA. Permanganate and acid is an OA. And what about ethanol? Ethanol is not on the chart. So if something doesn't occur on the chart, 1, we could ignore it, or 2, we can use some factual knowledge to figure it out. What is ethanol? Even though it doesn't occur on the chart, does that mean it's just too stable, unreactive, or what? What? A lot of these metals are highly flammable. When you buy a bottle of powdered metal, it gives you warnings, you know, flammable, highly flammable. Actually, do I have powdered metal? I should show you. I'll bring some powdered metal in. And powdered metal burns quite nicely. It burns because, what? Metals are combustible, right? The metals are this oxidation reduction stuff just takes repetition. It's hard initially, you know, but with enough repetition, then anything becomes easier, right? You know, the first time you do something, it's always hard. You just need practice. Problem is, some people don't like to practice. They leave it as hard. But some of these things you need to make connections with, you know? This is what I'm trying to do. I'm trying to make connections for you, but you need to start making those connections yourself by doing this repetitive stuff. And this repetitive stuff you think might not be so worthwhile, but it's incredibly worthwhile because that's how you can make connections. You know, metals are flammable because why? Because they're electron rich, they're reducing agents, etc. There's chemical properties of that. What about ethanol? Is ethanol very flammable?
Let's say, does ethanol burn more easily than iron or less? More. So ethanol is burned more easily than aluminum metal. You try to catch aluminum on fire versus ethanol on fire. Which one's easier to ignite? Which one do you think is easier to ignite? Ethanol. Ethanol is a strong, powerful, not oxidizer. This is the thing about drilling. You know, you got to do the drills. The same thing with nomenclature. You know, got to do the drills. And so this is basic knowledge. Basic knowledge is ethanol is a powerful reducer. Everybody should know that. It's standard. Methane. Is methane a powerful reducer? Even though it's not on the chart? Yeah, that's common knowledge. Common knowledge is... And so this is a reducer. Now, let's look at the reducers we have. What do you think is... we have two reducers. We have chloride ion and ethanol. Which one do you think is easier to catch on fire? Chloride ion, like in sodium chloride? Easy to catch sodium chloride on fire? No, it'll vaporize, but it's not going to catch on fire. It'll give you a yellow flame. Chloride's difficult. Chloride's such a weak reducer. Versus ethanol. Which one do you think is stronger? Ethanol. And so the strongest reducer is ethanol. The strongest oxidizer is permanganate and H+. Permanganate and H+ is easy because permanganate and H+ occur on the chart. And so all we have to do is consult the chart and then read it. You see, it's right here. Permanganate and H+. And so all we do is copy that reaction down. Permanganate plus 8H plus 5 electrons yields Mn2 plus 4H2O liquids. And so I just copied that right off the chart here. But shoot, ethanol is not on the chart. I know ethanol is the strongest reducer and it's a powerful reducer, but it's not on the chart. And so what can I do about ethanol? Okay, this is the people, the people who drill this over and over and over. They've done lots of skeleton redox. They've done this, they've done that, And they can easily make the connection. Oh, I saw ethanol before. I could figure it out, right? I know what the half reaction is. Have you seen ethanol before? No? I thought I did it. I didn't do it? No? Go back and look at the skeleton redox. What were the two reactants in skeleton redox? Did we do ethanol or did we do another one? We did ethanol? All right. What I see is I see a lot of potential for much better grades. You guys have a lot of potential to get much, much, much better grades if you did a little bit of review. Review to the point where, you've already seen it. Actually, when did we do it? Yesterday? No, Monday. So you've seen it more than once. Because, I'll tell you, most organics, when they're oxidized, they get oxidized to what? Soot, carbon monoxide, or carbon dioxide? we got a powerful oxidizer here. You should recognize that as a powerful oxidizer. So if we oxidize ethanol, what do we oxidize it to? Well, ethanol could be mildly oxidized to vinegar. It's possible. To acetic acid. But we don't have a mild oxidizer here. We have a powerful oxidizer here. Well, the same thing. Well, ethanol in wine is oxidized to vinegar because the oxygen level in the wine is so low. It should be very low. But we aren't going to worry about that. We're going to just predict the easiest. When you do a combustion reaction, like in Chem 4, when you combusted ethanol with O2, what did you write as the product? Carbon dioxide. Why didn't you write soot, carbon, or carbon monoxide? Because we assumed it wasn't the limiting reagent problem. We assumed that you had plenty of oxygen and just oxidized it all the way. Why didn't you oxidize it to carbon trioxide, carbon tetraoxide, carbon pentoxide, carbon hexoxide? Because those don't exist. And so the only logical ending place for this is carbon dioxide. Sure, we might get other products. It's true. Let's say we did this at low temperature. Let's say the concentration for permanganate in H+ was very low. Sure, we might get other products like acetic acid, soot, but the only thing is we just assume, heck, it's going to go all the way to what? And so we know it's going to go all the way to carbon dioxide. Now we can figure out the half reaction. These are all balanced half reactions, right? Can we figure out a half reaction? Sure. We have the skeleton redox method of figuring out half reactions, as long as we know what the major product is. And you should know what the major product of combustion or oxidation of ethanol is. It's going to be carbon dioxide. Think about your body. Your body, if you consume ethanol, it's not just excreted as waste. The ethanol is actually metabolized in your body. It's all redox, and it's going to produce carbon dioxide. Not only, ethanol ends up as carbon dioxide, but sugar. What do you think sugar ends up as? Sugar is what we call a carbohydrate. It has carbon, hydrogen, and oxygen. If you combust a carbon, hydrogen, oxygen compound or metabolize it, what do you end up with? Well, what do you exhale? CO2. So if you eat sugar, you're going to be exhaling CO2 because that's the final product of oxidation of sugar. Your body, the whole carboxylic acid cycle, all that metabolism is a whole bunch of redox. When you take if you take biochemistry, you're going to see redox reaction, reducing agent, oxidizing agent, NADH, NADH, whatever, NAD, all these oxidizing agents and all these reducing agents you got to memorize. Right? Biochemistry was a lot of memorization. Okay, so we can figure this out, right? This is called the hybrid method because, the other half reaction we can figure out by using the stuff we already know, etc. So I'm not going to finish this because this is exactly the same reaction we did for skeleton redox. Meaning for skeleton redox, we could have saved ourselves a step. In the skeleton redox thing, I could have just skipped the permanganate to manganese 2 because I already see it right here. Permanganate to manganese 2 is this. This is a balanced half reaction. I didn't have to do that. So I could have skipped that entire thing and just copied this down and then just did the ethanol to CO2. Saved myself some time on a test. And so if the half reaction occurs here and you have it on the test, why not use it rather than figure it out yourself? Okay, that's a hybrid method for redox. And then some of the redox are just hard to predict, then that's what we started off with. We started off with a skeleton. All right, now I want to go to acid-base. Acid-base reactions are even easier than redox, Bronsted acid-base reactions.
There are two types of acid-base reactions, Bronsted, Lowry. Bronsted-Lowry reactions is a proton transfer. The acid is what we call the proton donor or acceptor. The base Let's do this problem. I'm going to do potassium. What's this? What's this called? Potassium and this. Not hydro. Bisulfate? Bi or di? Bi. Sodium bisulfate is its common name. Its proper name would be sodium hydrogen sulfate. This, to me, looks like a double replacement reaction, right? The double replacement reaction, what are the products of this double replacement reaction? Yeah, good. Sodium phosphate and potassium bisulfate. And then we got to balance it. We'll need 3 of these and 3 of these, and then it should be balanced. Right? Is there a driving force for this? What were the driving forces for double replacement? No. Unfortunately, activity series is for redox. Only redox. We could have used the activity series, but activity series is too small. This is the activity series here. This is the upside down activity series, right? And the activity series goes to gold. See? And so the right side of this chart is an upside down activity series. The left side of that chart is a right side up activity series. Okay. It's for redox only, activity series. Activity series, you know what the activity series says? That the activity series says the driving force for a single replacement is going from a stronger reducing agent to a weaker reducing agent. You're only looking at the reducing agent in the activity series, and that's all. But it works because if the reducing agent goes from stronger to weaker, the oxidizing agent must go from stronger to weaker because of the conjugate relationship. That's the activity series in Chem 1A jargon. The activity series in Chem 4 is you go, higher and lower in the activity series, but get away from higher and lower. This Chem 4 thing. What's the driving force for double replacement? Did you guys even talk about driving force for double replacement? Precipitation or that kind of stuff? Do you guys do double replacements? Or just fuzzy? Double replacement should have been a major topic in Chem 4. I'm surprised. Because this semester, I'm particularly surprised. Because usually I get a lot more, response from the review. But take a guess. It doesn't matter. I'd rather have a guess than nothing. Yeah, solubility is going to tell you about precipitates. So, solubility rule number 1: all sodium salts and potassium salts, in fact, all group 1 salts are soluble. So these don't precipitate. Both of these will be AQ, AQ. So if I don't want to write AQ, I'll just leave it like that. Okay, then what else? We look at the solubility chart. Do you guys remember the solubility rules? If not,
You don't have to have them memorized next week, but you'll have to memorize them by exam 2. But the problem is, exam 2, what else are we doing? A lot of people think exam 2 is pretty tough. And so if you're spending a lot of time memorizing the solubility rules, you know, while you're trying to learn the other material, you know, that's why I introduced the solubility rules early, or at least I don't really introduce, I just tell you to memorize them early, so you don't have to do it at the same time with the other stuff. Because exam 2 is tough because of chapter 7. Chapter 7 deals with thermodynamics. At UCLA, they sell bumper stickers that say, I passed thermodynamics, because so many people failed that class. There's a debate. I was looking at a debate. There's a debate on at the Harvard website I saw, because I was just looking at some thermodynamics stuff, and I thought, oh, I saw some kind of interesting discussion. What's harder, thermodynamics or organic chemistry? And so there was a debate going on. And so that's exam 2. Well, anyway, I think I don't want to sound. I don't want to talk about study techniques anymore.
When will this reaction take place?
Yeah, but we need a driving force, and so the driving force for double replacement. We'll talk about it because we haven't gotten to double replacement. But essentially, there's no driving force here, so there's no reaction. But in this particular one, that's not the only type of reaction we look for. We look for other types of reactions like redox. You know, we look for redox reactions, and so we try redox. You know, even though automatically it looked like double replacement would do that, but it turns out there's no driving force for double replacement, but that doesn't mean a redox reaction or acid-base reaction won't happen. And so when we do redox, what do? We look at potassium ions, phosphate ions, sodium ions, and hydrogen sulfate ions. Right. And then potassium ions, oh, we have one more. What am I missing here? What am I missing? Water. That's what I'm missing here. And so potassium ions, phosphate doesn't occur on the chart, but you know, this is why we need some factual knowledge. Phosphate is a powerful oxidizer, you think? Well, one, is it an oxidizer? Yes. Why? Because of its oxidation state. Somebody tell me the oxidation state on phosphorus. +5. +5. So it should be like nitrate, a powerful oxidizer, right? But it isn't necessarily. Why would phosphate be a less powerful oxidizer than nitrate? There are reasons. You know, phosphorus is bigger than nitrogen, etc. But phosphate, you know, if you think this is a very common chemical, well, ethanol was a very common chemical, but, you know, ethanol doesn't occur on the chart because, you know, there's too many organics. All the organics are highly flammable. And so rather than writing ethanol, you'd say alcohols, you know, or you'd say carbohydrates. Carbohydrates are sugars, you know, carbon, hydrogen, oxygen. All those are flammable, right? You can burn sugar easily. You know, those are too much. So those ones don't occur on the chart because you know, factual knowledge. People should have that as factual knowledge. But phosphate, you know, phosphate's an ion like all these other ones. And, you know, in fact, phosphate, what do you think is more common? Phosphate or phosphate or ozone? Phosphate or gold-3? Phosphate or dichromate? Which one do you think, phosphate or, what was that, cerium-4? Phosphate or cerium-4? What do you think is more common? Phosphate is a common household chemical. And yet it's not on this chart, which tells me what? Likely that it's not a very strong oxidizer like nitrate. Nitrate's nitrogen plus 5. And so, yeah, I'd say phosphate's going to be an oxidizer. It's at the extreme, but, you know, not on the chart. Whereas ethanol was on the chart, I expect everybody to know that's a powerful reducer. I would expect people to not think of phosphate as a powerful oxidizer. Sure, phosphate can oxidize stuff, right? Because it is plus 5 after all. But its oxidation properties are probably not the most significant. Sodium ions. Oxidizing agent. HSO4 minus. Here we go. Here's sulfate. Sulfate, but this is 4H+. This is sulfate and strong acid. Well, here we have H+, don't we? But this H+ is attached because, you know, for this H+ to dissociate, this has to be a strong acid. Strong acids are strong electrolytes. HSO4 minus is what we call a weak acid. Weak acids are weak electrolytes, meaning that the H+ doesn't really dissociate. H2SO4 is a strong acid. This is a strong acid. This is not a strong acid. And so that H+ is stuck on there. And so this is, you know, we're missing something. We're missing H+. If we had a lot of H+ present, then we could probably use this reaction here. You know, because with sulfate in the presence of strong acid can be an oxidizer. But if we're missing the H+, do you think it's going to be as strong? No, why not? Have you made the connection? Why not? Why won't it be as strong? The H+, the oxidation state doesn't change. If H+ is missing, will it be as strong? No. Why not? Just give me one sentence. No, it won't give up as many electrons? No, that's not the reason. Not the reason. Tell me how you guys are approaching studying for the exam next week. Working through the homeworks, pretty much. Reading the chapter. Reading the chapter multiple times. It's not. Well, I said I'm not going to talk about study. We'll just see how it goes. Next week's exam. But it's because of water. We're not going to form water. It's not going to be as stable. And so this is missing H+, so we're going to form a less stable product, meaning it's not going to be as reactive. This is an OA and RA. And so we pick out the strongest OA. The strongest OA will be, well, all these are really insignificant. Probably the strongest OA might be phosphate, but phosphate's not on here, so we'll just use the next best one. Strongest OA, well, there's sodium. It looks like water. The strongest RA, it looks like water. So the reaction would be the strongest OA is water, the strongest RA is water. We add them up. Two things. You can say, will water react with water in a redox reaction? Well, we could save ourselves some time. If water reacts with water, in the first reaction we form hydrogen. In the second reaction we form, here, we form oxygen. And so if water reacts with water in a redox, we're going to form hydrogen and oxygen. Do you think there's going to be a driving force there? No. And so I'm going to save myself some time. I could write it all out, but by the time I get to the end of it, we'll see that there's no driving force. And so we tried double replacement, we tried redox. Now we're going to try acid-base. Acid-base is the same as redox. One, we inventory solution. And so when we inventory, we have potassium ions, phosphate, sodium, HSO4 minus, and water. Then we consult the chart. Basically, it's the same as redox. We consult the chart, except we don't consult the redox chart, we consult the acid-base chart. Acid-base chart is the same kind of deal as a redox chart. This is a chart of acid and base strengths. And so, looking at the acid-base chart, we go, are potassium ions a good proton donor, proton acceptor? No. And so what we call those are neutral, N. Neutral. Phosphate is a base. Sodium ions, neutral. HSO4 minus is an acid and a base. HSO4 minus is what we call amphoteric. H2O liquid is an acid and a base. It's amphoteric. H2O liquid goes both ways easily. HSO4 minus is a much better acid than it is a base. In fact, it's an awful base. Some people don't even consider it as a base. But it occurs on both sides of the chart, so we'll use it. So we pick the strongest base out of these. The strongest base is going to be phosphate, looking at the chart. Phosphate's borderline, what? Strong base. Borderline strong base. Actually, let's see if I have an acid-base chart I can bring up here. I'll make it a little easier. Let's see. This has the conjugate relationship also. And so if you look, hydroxide is a strong base. Actually, there's stronger bases than hydroxide. Like those. Could you tell me two bases that are stronger than hydroxide? Not NH3, NH2. NH2 minus is the strongest base on that chart. Do you know its name? Probably not, because it's called amide, A-M-I-D-E, NH2 minus, amide. Strongest base on that chart. Followed by oxide, you should know that, and hydroxide. Look where phosphate is. Even though phosphate is considered a weak acid, it's not terribly weak. And so here, this is a base. What's the strongest acid present? HSO4 minus. The acid-base chart has a conjugate relationship also. You can see HSO4 minus here. Do you know HSO4 minus is almost borderline and a strong? Well, it's still kind of a ways. We have oxalic acid here at the border. Oxalic sulfurous, then the hydrogen sulfate ion. Okay, then what we do is we either write the equations down. You know, you can write the equations down if you want. We copy the equations off the chart. Phosphate plus H plus yields HPO4 2 minus. And we copy the other equation down. HSO4 minus. Okay, this HSO4 minus is tricky because HSO4 minus occurs on both sides of the chart. Here it occurs as an acid. Here it occurs as a base. So we've got to make sure we write the right one. And that is, it occurs as an acid here. H plus sulfate. Phosphate is only a base, so there's only one equation. HSO4 minus, we had a choice.
And we knew it was this one because we chose it as the acid. And then what we do is we combine it. This is easier than redox. Because the reason it's easier than redox is because all those reactions, do you notice a pattern? All these reactions only have one proton transfer. All of them. Whereas in the redox chart, where is the redox chart? In the redox chart, the number of electrons transferred varies from 1 to 5. And so we're transferring anywhere from 1 to 5 electrons on the redox chart, but on the acid base it's all 1. And so we never have to multiply these. We just add it straight. And so the protons gained is equal to the protons lost. So the net reaction is phosphate plus HSO4 minus yields HPO4 2 minus plus SO4 2 minus. We make sure everything's balanced. It is. And then we look for driving force. So we're out of time. What do you think the driving force is for acid base? The same as redox, except not stronger oxidizer. We're going from stronger acid, stronger base to weaker acid, weaker base. What's the easiest way to figure out the conjugate relationships? That is the reverse, is look at the half reactions. In this case, this is acting as the acid going backwards. In this case, this is acting as the base going backwards. And so we can get it there. Yes? How come perchloric and chloric acid are not here? Because this table is very short. It's not extensive. This has been this is called the annotated version. That is, they chop a lot of stuff out of here to keep it simpler. Those are.